questions from heat capacity and specific heat. And if we basically consider something like heat capacity, we can say that it is the amount of heat energy that we need to raise the temperature of a substance by 1 degree Celsius. Let's say I want to give some heat so that the temperature ranges from 100 to 101 Kelvin. So for that, how much heat do I need? That is something which is called the heat capacity. So there is a difference between specific heat capacity and heat capacity. So in heat capacity, we have only the temperature and the amount of heat required. But if we are basically considering something like a specific heat capacity, the difference is more important. It means that I want to raise the temperature of one unit mass of a substance. Like for example, I want to raise the temperature of 1 kg or 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. Then I basically call it as specific heat capacity. Okay, so these are the basic differences. In terms of formula, you can see heat capacity is denoted by capital C. Okay, and it's Q divided by delta T because there is no amount of substance involved. But specific heat capacity is actually denoted by small c, and here we have got Q divided by delta T, the same thing, but there is a mass involved. That means the mass of the substance, and the mass of the substance will be in kilogram. Okay, so this is specific heat. uh, Basically heat capacity is something which will depend on the amount of substance. Quite obvious, if I have 10 kg of a substance and I want to increase the temperature, then it would be amount of substance which will decide how much heat do I need. But specific heat is not that, it's per unit mass. So even it might be 10 kg, I just need to know how much heat do I need to supply for increasing 1 kg, the heat required to increase the temperature of 1 kg of the substance. So that's why specific heat can be considered as an intensive property, and it is more or less constant. And heat capacity is something which is not a constant. So in general, whenever we are doing numericals or we need the value, specific heat is more logical. Okay, we are going to use it because there are specific heat values for any material that more or less we have. Okay, a relation also you can easily find out. You can see that this small c is equal to Q by delta T into M, and Q by delta T is capital C. So accordingly, I can write down this relation as well. Okay, so they are connected. একটা মানে mass এসে যাবে, that's the important part. Okay, so from now onwards, we are not going to talk about heat capacity. We are going to talk about specific heat capacity because this is mathematically more important. It tells the property of the material as well. Okay, so specific heat capacity is something which we are going to look into. So if you're basically considering the specific heat capacity when the volume is constant, we usually denote it by Cv. Okay, and if the pressure is constant, we consider it as Cp. And please remember, this relation is very important, which you are also going to derive. This is also there in your syllabus. Cp minus Cv is equal to R, is the molar gas constant. So if you consider any specific heat of any gas molecules, okay, and you divide Cp by Cv, you are going to get something which is okay. If we get it something like this, we basically say that if we take the difference between the Cp and Cv for any element, it is always a constant, which is nothing but molar gas constant. So this is what is there. Okay, and don't get confused with this. This is del U by del T. So if we've seen this, the specific heat is nothing but the amount of heat divided by mass into temperature, right? So dt, let's say dt. So if we go into the first law of thermodynamics, okay, we know dq is equal to du plus pdv, or work done, right? Pdv. Okay, pdv. Now it's saying that it is at constant volume. So if it is constant volume, means this dv will more or less become 0. Now if this becomes 0, that means dq and du are the same. So in place of dq, specific heat is heat per unit amount of heat required to raise the temperature by 1 degree centigrade per unit mass. So that means in place of dq, I can write down du when we are considering constant volume. So I'll just write it down as du divided by unit mass. So I can just consider it to be 1 and divided by dt at constant volume. Okay, So this is what is specific heat, and this is how this relation is derived. Okay, I've not written it, but this is something which is there. Apart from that, at constant pressure you can also think about the same thing, but at constant pressure what happens is dq will remain as du plus pdv. Nothing is going to change, because even if pressure is constant, this will remain. So there is no zero term, so it is du plus pdv, and we're just denoting it by del h. Okay, we're going to look into that later. There is a term which is actually called enthalpy, and enthalpy is a relation which connects the internal energy and volume with pressure. Okay, so this is the relation, so we're just writing it down as del h, but in place of this you can also write down del q del t at constant pressure. Doesn't make a difference if you want to explain this. Okay, now basically for an ideal gas, that means pv is equal to rt. Ideal gas jokhoni bolbe, just think that the relation pv is equal to nrt is valid. Pv is equal to nrt is valid. So that means this is an ideal gas, and for this cp minus cv is equal to 0, which is important. So next is unit of this specific heat and heat capacity. I think it's very simple. Heat capacity is delta q by delta t. So joule per Kelvin. Q mane heat unit is joule. Okay, energy units per Kelvin. You can also take it as calorie per degree centigrade and so on. Okay, but SI or standard unit is this. So let's follow this. Next we have got something which we call a specific heat capacity. So it is joule per Kelvin, no doubt, but then there is per unit mass, so maybe 1 kg. So I'll just take it to be kg. So this is joule per kg Kelvin. So this is the unit of specific heat. These are some values, but sometimes what happens is you'll be given numerical problems, and in numerical I think this will be provided. Okay, most of the time it's provided, but some of the values I think we should remember. At least for water we should remember. It is 4186 joule per kg Kelvin. Okay, you can convert it to calories and all, but this is the thing that you should remember: 4186 SI unit, 4186 joule per kg Kelvin, right? You can see that this is the value of specific heat and not heat capacity, because heat capacity will depend on mass. Specific heat capacity does not depend on mass, it is per unit mass. So this is the value. For ice you can see it is less. Okay, so that means if I want to raise the temperature of ice by 1 degree, I need to give less energy compared to water. Okay, copper is a very good conductor, we already know, and if you basically consider a metallic body, let's say for made of copper, and on the other hand you consider something which is made up of, let's say, ice. Okay, then what happens is for heating the ice you need to apply more energy, you need to supply more energy or more heat, but for heating copper you need less heat and it will easily get heated up, right? So it directly comes from the idea of specific heat capacity. It is directly an implication of specific heat capacity, and that is why this is important. So these actually can be used to design heat sinks and all, where you basically need that the temperature should not increase all of a sudden, or it should cool down slowly. So these kind of system can be actually designed if we know the specific heat of that particular system. Okay, so be it in engineering, climate science, or everyday use. For cooking we usually don't use something which is an insulator. We use iron utensils or steel utensils, right? It gets heated up very fast, so it's more easy to cook there. So that is the reason that we are basically using those things. Okay, so we can find out the relation of cp minus cv is equal to r. It's not that complicated, we can do that. So for that what we can do is we can first find out some relations here. First thing is q, heat. Okay, so if you're basically considering a constant volume, we can say dq is equal to du. Okay, so there is no such thing as dw, because pdv, work done, is 0 with constant volume. So we can say it's delta u. Okay, if we're basically considering the total heat. Okay, or delta u is equal to q. Okay, now if I write down q is equal to delta u, now just now we have seen that the specific heat at constant volume is equal to del u divided by del t. Okay, and if you're basically considering only 2 points, okay, a small change, you can write it down as delta u divided by delta t. Okay, so that means I can write down this delta u, or let's take this m also now, mass. If we take this mass m, this is the definition of specific heat. So delta u would be cv into m into delta t. So this is what is done here, m into cv into delta t. Okay, so q is the heat added to the system, delta u is the change in internal energy, and cv is the specific heat at constant volume. So these relations are very important, and it's quite obvious that these things will be there. Okay, next what we have here is the basically whatever we are going to do or doing here, it's basically for an ideal gas. Okay, if we have the specific heat at constant volume, del u del t at v, okay, these things are for ideal gas. Now let's look into the pressure term. Pressure term also, we know that there is no change in the first law of thermodynamics. It will be dq is equal to du plus dw, or q is equal to delta u plus p delta v. Okay, so what we are going to do is q is nothing but the specific heat at constant pressure. Okay, so if we consider the specific heat at constant pressure, what happens is we can simply write it down as q is equal to constant pressure money, we can directly take it to be delta q divided by delta t, or dt, right, or dq by dt, or we can write it down as delta q divided by delta t. Now what is my delta q? That is from the first law of thermodynamics, that is nothing but delta u plus p delta v. Let's take m here, m delta t. This is my q. Okay, or we can also write it down as sorry, this is not q, this is cp, specific heat at constant volume. This is cp. So that means cp into m delta t is this relation, so that's why we written mcp into delta t is equal to this relation. So this is what we have for this. Next what we can do is we can find out what is the relation between cp and cv. So let's try to do that. For cp minus cv, it is nothing but r. So if you take these relations here, okay, we can actually use these relations. Okay, but before that we are just doing it. Okay, let's see this is we are going to derive it now. Now the first thing is what is gamma. Okay, there is a term which is actually called gamma, and gamma is actually called as the specific heat ratio. This is very important. Gamma is called the specific heat ratio. That means if you know the specific heat at constant pressure, and if you know the specific heat at constant volume for a molecule, you can find out what is the ratio between them, that is cp divided by cv. Okay, so this is very important again. This particular value that we are seeing here comes from the law of equipartition of energy, which we are going to look into that later. But right now I'd like to tell you that you need to remember these two values. Okay, just a second, I just need to remember these two values because these are important. So what happens is, if you consider a monoatomic gas, the specific heat at constant volume is fixed. It is 3 by 2r, right? So we basically consider a molecule which is single, right? Let's say nitrogen molecule. So it is just 3 by 2r. If you're basically considering a diatomic molecule, that means there are two atoms involved. The specific heat would be 5 by 2r at constant volume. On the other hand, if you're basically considering the specific heat at constant pressure, for monoatomic it is 5 by 2r, and diatomic it is 7 by 2r. Okay, we should remember these results because these are used every now and then. You might have some questions as well, MCQ, objective, whatever. We can also take the ratio between them, that is cp by cv, which is actually gamma. So we'll take cp on top, this value, and cv at the bottom, this value. So it will be 5 by 3. For this it will be 7 by 5, so and so on. Okay, so these things are important. These things you should take there. Next, let's derive this cp minus cv is equal to r. Okay, so for this we have already done partially the work. Okay, we have already said that delta u is equal to n cv delta t. Okay, if we are considering the relation for cv, n cv delta t, this we have derived just now. And for pressure we have seen that it is q is equal to n cp delta t. Okay, now if we basically consider an ideal gas, pv is equal to nRT, and if we have to see a small change in volume, I can write down delta v is equal to nr delta t divided by p. Okay, so this is there, and this is the equation for an ideal gas, change in volume at constant pressure. This is something which is needed because we have delta t terms here. okay, and we want to show that it's Cp minus Cv is equal to R, so we have to somehow bring R in the equation, right? So that's why we are writing it down like this, so that we also have an R here. Okay, now let's want to find out the work done, okay, during expansion. So work done is nothing but P delta V. Okay, these are the steps that you have to follow basically. And so P into delta V is, just now we have seen, nRT into divided by P. So that means it is P into nRT delta T by P. This PP will get cancelled, so this would be nothing but nR delta T. So this is the work done that we have. Okay, next let's go back to the first law of thermodynamics. First law of thermodynamics says that Q is equal to delta U plus W. W we have just now found out, it is nothing but nR delta T, so we'll replace it with nR delta T. Delta U we have found out as nCV delta T, and Q we have found out as nCP delta T. So you see delta T are there in all the three terms, so delta T will get cancelled, n and n will get cancelled, and I will be left out with Cp is equal to Cv plus R, or Cp minus Cv is equal to R. So this is basically a very simple derivation. Many a times what you can do is, you don't need to do the previous things first. You may start with this equation itself. Just write down this equation and say from the first law of thermodynamics we have got Q is equal to delta U plus W. Then you have to find out what is W. So we know W is equal to P delta V, right? And we know for an ideal gas PV is equal to RT. So let's write it down as P delta V is equal to nR delta T. Okay, I'm just showing everything in one line here, it will be more easy for you to remember. So that means delta V is equal to nR delta T divided by P. So this is the work done relation. So that means I can simply write it down as P into this, so I can simply write it down as nR delta T. So you can just replace this nR delta T here, and then you can find out what is the specific heat at constant volume and pressure. So for constant volume, we'll just go with the definition. Definition tells me that it is nothing but dq, so let me write it down as delta Q divided by m into delta T, right? And that means I need Q, so Q, okay, simple, delta Q is equal to mCV delta T. Okay, but then the thing is, it is basically delta Q is equal to delta U plus P delta V. Now we are considering constant volume, so that means this will become 0. So that means delta U is equal to mCV dt. So I can just replace this delta U with mCV dt. Okay, m or n, whatever, nR delta T. Similarly, you can do it for Q. Q is more easy. Q is directly this, Cp is equal to delta Q by m delta T, or delta Q is equal to mCp delta T, so mCp delta T. So this terms gets cancelled, and this is Cp minus Cv is equal to R. This may be a question for maybe 3 to 5 marks. Okay, maybe sometimes you need to explain these things, that's more important. So this is how you can, apply or use this to do. Okay, so this basically, as a relation which will apply only to ideal gases. Ideal gases, it simply means that the gases which are actually following the equation of PV is equal to nRT. So this is specific heat, all about specific heat, and also what is the relation between Cp and Cv. Carnot engine we have done already in the last class. Okay, and I was just going through some numericals. Maybe we can just check again. These things are all done, completed. Okay, this is done. This is a question which you might check. Yesterday we have done the Carnot cycle, and we have found out some relations for work done. Now basically, if you basically have an adiabatic process, you can straight away use this relation for work done. You don't need to use PF, VF, PI, VI. You can just take it to be final minus initial, that is okay. P2, V2 minus P1, V1. So if you look into the question, it states, says that pressure is given, volume is given, the volume final is given, and the specific heat ratio is given. You have to calculate the work done. But then if they don't mention whether it is an adiabatic process or not, you might be a bit confused. But they have mentioned it adiabatic process, so straight away use this relation. That's it. Now in this relation, you need P2, V2. Now you see V2 is given. Okay, P2 is not given. P1, V1 is given. P1 is given. V1 is given. Okay, so that means first thing is first, I need to find out what is V2, and gamma is given, so gamma is also not needed. Now in order to find out V2, okay, we can simply use this relation of PV to the power gamma is equal to constant. Now yesterday I told you if I say PV to the power gamma is equal to constant, that means P1 V1 to the power gamma is equal to P2 V2 to the power gamma is equal to P3 V3 to the power gamma. When you multiply these two quantities, you are more or less going to get it always as a constant value. So from here you can say P2 is equal to P1 V1 by V2 to the power gamma. Just multiply this term, use the value of gamma as 1.4, multiply, and you are going to get the result as this. Okay, so let's say this is my value of pressure 2, okay, and I can put it here. I've written it in not Pascal but kilopascal, because here this is in kilopascal. So if I write down this also in kilopascal, I can put the value, okay, and do my calculations more easily. Okay, since it's a ratio, so it's not going to affect the final result, just the difference. Even if you write it down in Pascal, the difference will remain the same. So this is 61 joule. Okay, so work done is 61 joule. So that means the work is done by the system, because it is positive. If it was negative, work was done on the system. So these things also we have to look into. Okay, like compression, like this is an adiabatic expansion rather, because you can see that your volume 1 was 1 liter, it became 2 liter. So when it becomes 1 liter to 2 liter, that means it's an expansion, and if it's an expansion, your work done must be positive, because if you have got negative, that means some mistakes have been there in your calculation. So please make sure that those things are actually noticed. So let's come back to the today's topic. The topic is specific heat and heat capacity. So in these also there might be some numerical questions. Many a times some values would be given. For example, this case, like a 2 kg block of aluminum. Now you are dealing with a problem where you are supposed to find out the heat required. So the specific heat capacity would be given. So for aluminum, the heat capacity is 900 joule per kg Kelvin. It's given. Is heated from 20 to 70 degrees centigrade, and you have to find out what is the heat that is required. Okay, so it's simple. I can directly use this relation, Q is equal to mc delta T. So even if you don't remember the relation, you know the original relation of specific heat. Think about it, derive the relation, and then you can do your calculation. It becomes more easy. M is 2 kg given, C we already know what is given, delta T is nothing but the change in temperature, 70 minus 20, which is 50. So you can multiply them and you can get the answer as 90 kilojoule, right? So this is a very very simple question, but you need to know the relation. Here also Cp is given, Cv is given, and you know that R value is 8.314. So every time Cp minus Cv is there, the value will always become 8.3 or in that range. So it is 8.3, obviously, just verified. Okay, it's just a simple question. These questions might not be there. This may be important. Okay, these kind of questions in Carnot cycle. A Carnot engine operates between TH is equal to 500 Kelvin and TL is equal to 300 Kelvin. That means TL and TH, you can easily find out the efficiency using the relation eta is equal to 1 minus TL by TH. So this is already done as soon as you look into these values. So efficiency of the engine to pehle nikal gaya, it's very easy. Next question is what is the work done. Now when we look into the work done, it is nothing but eta into QH. So if you know what is the efficiency, efficiency simply means that how much of the supplied heat is converted into work. So 40% of the supplied heat is converted into work. So that means if you know what is the heat supplied, that is 1000 joule. So that means it will be 1000 joule, 40% of 1000 joule, and 40% of 1000 joule is 40 by 100 into 1000. So that means 0.44 into 1000, so it is 400 joule. So that is the work done. So you don't need to think that what was the relation, how do I get V and volume and so on. You don't need, because you know the efficiency. You can find out the work done if you know what is the amount of input heat that is being supplied. Heat rejected is also very simple. The amount of heat that is given is 1000 joule. The amount of heat that is converted into work is 400 joule. That means 600 joule is rejected, because that much heat is not used. It is rejected into the cold reservoir. So it would be 600 joule. Okay. So these kind of questions are common. Okay. You might get these kind of questions as well. Okay. One more topic which might be important, is something which we call as second law of thermodynamics. Okay. Second law of thermodynamics is again different. You have more numericals from the first law, and the applications are also there from the first law. Second law of thermodynamics has got two statements mainly. One is actually called the Kelvin-Planck statement, and the second one is called Clausius statement. But it mostly says that you cannot basically have a 100% efficient engine. It's just like an application of the Carnot's engine. Okay, Carnot's engine says that this is the maximum efficiency that you can have, and the second law tells us that you cannot have an engine which is more efficient than the Carnot engine. Okay, so this is just a way of stating Carnot cycle, that's it. So it states that it is impossible to construct a heat engine that operates in a cycle and converts all the heat absorbed from a heat source into work without rejecting some heat to the cold reservoir. So this is a statement given by Kelvin Planck. So sometimes the questions may be that write down the Kelvin Planck statement, or write down the Clausius statement, or write down the second law of thermodynamics. So if they just tell you second law of thermodynamics, it's better to write down both the statements. And it does not mean that it has to match word by word. Okay, some words may be here and there, but more or less the essence is that it should be meant in that way. So this talks about heat engine, and the Clausius statement says that the heat can only flow from a hot body to a cold body and not from a cold body to a hot body, and that's quite obvious. You basically have a temperature around in your room, maybe around 25 degrees centigrade. You got a hot cup of coffee at around 50 degrees centigrade. It's not that the heat will come from the room and the temperature of the cup will rise from 50 to 55. That's not possible. Not from cold to hot, right? It will be like the temperature of the tea at 50 will get down to room temperature eventually. It will come back to 25. So this is what is the idea behind Clausius statement. Okay, heat is transferred from a colder body to a hotter body without the input of external work. So this is important. Entropy statement is not that popular, okay, but we are going to look into the concept of entropy, that is important. So entropy is something which tells you how disordered a system is. Like if I keep on supplying heat to a system, the system will become more and more disordered. Let's say I have got some gas molecules, I give some input, heat input. The molecules will start vibrating more vigorously and it will become more and more disordered. So entropy is a measure of disorderness. In general, in the universe, the entropy will keep on increasing forever. Okay, as the universe keeps on expanding, the entropy also keeps on expanding. And the relation for entropy, basic relation is this. Okay, dq by t. That means total temperature, and on top there is nothing but the change in the heat. Okay, so this is something which is there. In general, if you look into the practical things, there is something which we call as irreversibility. Okay, any process which is natural, okay, it's a natural phenomena, this will never get back to its original state. It is more or less irreversible. Like the heat flows from hot to cold, you're not going to make the heat go back from cold to hot again, okay, until and unless you use some external source or energy and all. Okay, naturally it's not going to happen. And that is why in the world or in universe, the entropy will keep on increasing forever. Okay, it's not going to get back to the same state. So this idea of entropy is actually there in heat engine also. Okay, second law of thermodynamics, that means the Clausius or the Kelvin Planck statement, is nothing but directly used in heat engine. We've already seen that. Okay, if you consider heat engine, that means we're basically using the heat to do some work. Refrigerator on the other hand is something which is just the opposite. Okay, it usually cools down a system. That means it is going to reject heat. Okay, it has to reject more and more heat so that something cools down. And if we say efficiency of a heat engine is eta is equal to 1 minus TL by TH, for refrigerator it is something which is called coefficient of performance, or COP. For refrigerators, this coefficient of performance is nothing but written as QL divided by W. Or we can say whatever is heat is rejected divided by the work done. Okay, this is the coefficient of performance for a refrigerator. Okay, the fridges and all these things are basically working on this. We're not going to look into this now, right now, or not the proof actually. Just going to look into the idea here. So this is something which is called the Clausius inequality. So if we want to represent the second law of thermodynamics mathematically, we can actually represent it like this. Okay, what it means is that the entropy will always be less than or equal to 0. Okay, this is basically for any kind of cyclic process. Cyclic means you're going to get back to the same state. Okay, so this is what is the basic interpretation is. Okay, so if you basically consider a reversible cycle, that means the entropy will come back to the same state. It does not happen in actual reality, right? It is something which is an ideal case. Exact reversibility is not possible. So if this becomes 0, That means for an ideal case we can say that it is a reversible process. Okay, for an irreversible process obviously it has to be less than 0. Okay, so negative entropy. Okay, the disorderedness will keep on increasing. Okay, as we keep on giving the heat, the entropy will keep on changing and so on. So it basically says that if you're basically considering a reversible process 0, if it's a non-reversible process it is always negative. Okay, derivations we are not going to go into that. Okay, these things we have already seen. That's just the definition. Then if someone asks you what is the definition of entropy, so you can simply say that entropy is a thermodynamic property that measures the degree of randomness, disorder or energy dispersal in a system. So if an energy is being given out from a system, it involves more and more disorderness in the system. So if we can measure how much energy is given out by the system, we can also measure what is the disorderedness in that system. Okay, so whatever energy is being given out by that system, that cannot be actually, we cannot get it back to do some useful work. Okay, so that's again very important. The useful work needs to be done, so that's there. Okay, next we have something which we call as the entropy's physical significance. Okay, as I said, entropy simply means that how disordered a system is. So if you basically consider gas molecule system, this entropy directly fits in to understand it better. Okay, and we basically talk about reversible and irreversible process. If we consider a reversible process, which is exactly not true every time, the entropy will always remain constant. Okay, so these are some normal things that happens. Okay, something which is related with universe as well. The total entropy of the universe is always increasing, which aligns with the second law of thermodynamics. Okay, it's never going to decrease, it will keep on increase. That means the randomness that is there is going to keep on increasing. So these are some examples. I'll share the PDF, you can go through. Okay, okay. So if we basically consider different processes like isothermal, adiabatic, isochoric and isobaric process, for all of them we can actually find out the entropy, and we can check this one by one. Okay, if the temperature remains constant, we are talking about an isothermal process, we can write down the entropy as integration of delta Q divided by T. Temperature is anyway constant, it can come out, integrate delta Q, you are going to get Q. But we know what is Q for an isothermal process. The Q and work done are equivalent because there is no change in temperature, so internal energy is 0. So whether you write down Q or W, it's the same thing. We have already found out what is W, nRT ln of Vf by Vi. So that means delta S can be written as nR ln of Vf by Vi, because there is a T here, there is a T here, that will get cancelled, and this is the entropy. So if someone tells me to find out the entropy for an isothermal process, I just need the initial volume and the final volume, that's it, and then I can find out what is the entropy of the system. If I know the number of moles, obviously if the number of moles are more, the entropy will also be more gases, more disorderedness and so on. Similarly we can do it for adiabatic process also, but adiabatic process method there is no heat change, no heat transfer, so the entropy will always remain as 0, right? Or delta Q by T, that means integration of delta Q by T, but delta Q is 0 because there is no change in heat or exchange of heat, so this will more or less become 0. So entropy will remain constant for a reversible process. So this is a adiabatic process. So for all of them you should know what is the work done or the heat. Okay, for isobaric process, that means if the pressure remains constant, we have already derived it when we derived Cp minus Cv is equal to R. This is my heat, Ncp delta T. So delta S is equal to delta Q by T or Ncp dt by T. So since it's a isobaric process, pressure remains constant, does not necessarily mean temperature remains constant. So Ncp can be taken out, and this is ln of T, and then we can put the limits, let's say initial and final, so it is Tf divided by Ta. So this is the entropy in case of isobaric process. Isochoric process also we can do it, right? That is Ncv delta T. So here also we are going to do the same thing. The relation for entropy for isobaric and isochoric process looks similar. See, Ncv ln of Tf by Ti, because isochoric process volume constant, isobaric pressure constant, and Cp ln of Tf by Ti. So the relation is more or less similar except Cp and Cv. Okay. uh, one more important thing is something which we call as phase transition. Phase transition means you have water, it becomes ice, okay, or you have ice, it becomes water, and then it becomes steam. So these are all phase changes, okay, changes from one phase to another. And for that, we can actually use the concept of entropy. From entropy, we have got delta S is equal to delta Q by T, and if there is a phase transition, the heat actually can be calculated by the relation delta Q is equal to M into L. So if there is a phase transition, we basically need this value of L, which is dependent on whether it is going from solid to liquid or from liquid to gas and so on. Okay, so this is called the latent heat. So if you know the latent heat, we can actually find out Q, delta Q is equal to ml. So entropy can also be written as ml divided by T if there is a phase transition as such. Okay, this is not needed. Irreversible process, cyclic process, it is zero. We have already seen this. Okay, so I made this table. Go through this. Okay, I'll share it with you. Go through this. These things will help you. Okay. So this is all about entropy. A numerical question might be something like this, where someone tells you that there is a process which is isothermal in nature. You have to find out the entropy. That means you can directly use the relation which you have just now seen. Delta S is equal to nRVF by Vi. As I told you, I just need the final volume and the initial volume. I know the value of R and I need to know how much is the mole. Okay. Temperature is not required, whatever may be the temperature. The fact is it is isothermal, so temperature does not play any role. You can directly put the value and do your calculation. So this is what you get. Entropy change in isobaric process, same, use the formula, look into the question. Okay, so it's easy. Isochoric process, so these are directly applications of the formula. Okay, entropy in phase change, so look into this is interesting question. If you know the formula, it's a cakewalk. If you don't know the formula, then it will become difficult. So 1 kg block of ice at 0 degree melts into water at 0 degree, so it becomes water. Okay, from ice to water. So you need the latent heat. Okay, latent heat is nothing but 334,000. This will be provided to you. This is the latent heat of fusion of ice, right? So it becomes ice to water, so fusion of ice, this is the value. So directly put the value of L as this. Mass is given as 1 kg, so you can take M into L, multiply. Temperature is given as 0 degree centigrade. So 0 degree centigrade means you have to convert it into Kelvin, because this latent heat value is joule per kg and you are doing everything in SI. So let's convert it into Kelvin. So it will be 273 Kelvin. So that means this will be nothing but this much value. Okay, so this is the entropy when we are basically considering phase change. Okay, so these are the things which are important, and with this I think entropy is covered.